My name is Jada of Jaded Company, and we are going to start Chapter 2 of the complete reference to Java 9th edition. Chapter 2: An Overview of Java. As in all other computer languages, the elements of Java do not exist in isolation. Rather, they work together to form the language as a whole. However, this interrelatedness can make it difficult to describe one aspect of Java without involving several others. Often, a discussion of one feature implies prior knowledge of another. For this reason, this chapter presents a quick overview of several key features of Java. The material described here will give you a foothold that will allow you to write and understand simple programs. Most of the topics discussed will be examined in greater detail in the remaining chapters of Part 1. Object-oriented programming. Object-oriented programming is at the core of Java. In fact, all Java programs are at least some extent object-oriented. OOP is so integral to Java that it is best to understand its basic principles before you begin working with even simple Java programs. Therefore, this chapter begins with a discussion of the theoretical aspects of OOP. 2 paradigms. All computer programs consist of 2 elements, code and data. Furthermore, a program can be conceptually organized around its code or around its data. That is, some programs are written around what is happening, and others are written around who is being affected. These are 2 paradigms that govern how a program is constructed. The first way is called the process-oriented model. This approach characterizes a program as a series of linear steps, that is, code. The process-oriented model can be thought of as code acting on data. Procedural languages such as C employ this model to a considerable success. However, as mentioned in Chapter 1, problems with this approach appear as programs grow larger and more complex. To manage increasing complexity, the second approach, called object-oriented programming, was conceived. Object-oriented programming organizes a program around its data, that is, objects, and a set of well-defined interfaces to that data. An object-oriented program can be characterized as data controlling access to code. As you will see, by switching the controlling entity to data, you can achieve several organizational benefits. Abstraction. An essential element of object-oriented programming is abstraction. Humans manage complexity through abstraction. For example, people do not think of a car as a set of tens of thousands of individual parts. They think of it as a well-defined object with its own unique behavior. This abstraction allows people to use a car to drive to the grocery store without being overwhelmed by the complexity of the parts that form the car. They ignore the details of how the engine, transmission, and braking systems work. Instead, they are free to utilize the object as a whole. A powerful way to manage abstraction is through the use of hierarchical classifications. This allows you to layer the semantics of complex systems. breaking them into more manageable pieces. From the outside, the car is a single object. Once inside, you see that the car consists of several subsystems: steering, brake, sound system, seat belts, heating, cellular phone, and so on. In turn, each of these subsystems is made up of more specialized units. For instance, the sound system consists of a radio, a CD player, and/or a tape or MP3 player. The point is that you manage the complexity of the car, or any other complex system, through the use of hierarchical abstractions. Hierarchical abstractions of complex systems can also be applied to computer programs. The data from a traditional process-oriented program can be transformed by abstraction into its component objects. A sequence of process steps can become a collection of messages between these objects. Thus, each of these objects describes its own unique behavior. You can treat these objects as concrete entities that respond to messages telling them to do something. This is the essence of object-oriented programming. Object-oriented concepts form the heart of Java, just as they form the basis for human understanding. It is important that you understand how these concepts translate into programs. As you will see, object-oriented programming is a powerful and natural paradigm for creating programs that survive the inevitable changes accompanying the life cycle of many major software projects, including conception, growth, and aging. For example, once you have well-defined objects and clean, reliable interfaces to those objects, you can gracefully decommission or replace parts of an older system without fear. The 3 OOP principles. All object-oriented programming languages provide mechanisms that help you implement the object-oriented model. They are encapsulation, inheritance, and polymorphism. Let's take a look at these concepts now. Encapsulation. Encapsulation is the mechanism that binds together code and the data it manipulates, and keeps both safe from outside interference and misuse. One way to think about encapsulation is as a protective wrapper that prevents the code and data from being arbitrarily accessed by other code outside of the wrapper. Access to the code and data inside of the wrapper is tightly controlled through a well-defined interface. To relate this to the real world, consider an automatic transmission on an automobile. It encapsulates hundreds of bits of information about your car, such as how much you are accelerating, the pitch of the surface you are on, the position of the shift lever. You, as the user, have only one method of affecting this complex encapsulation. By moving the gear shift lever, you can affect the transmission by using the turn signal. You can affect the transmission by using the turn signal or windshield wipers, for example. You can't affect the transmission by using the turn signal or windshield wipers, for example. Thus, the gear shift is a well-defined, indeed unique, interface to the transmission. Further, what occurs inside the transmission does not affect objects outside of the transmission. For example, shifting gears does not turn on the headlights. Because an automatic transmission is encapsulated, dozens of car manufacturers can implement one in any way they please. However, from the driver's point of view, they all work the same. This same idea can be applied to programming. The power of encapsulated code is that everyone knows how to access it and thus can use it regardless of the implementation details, and without fear of unexpected side effects. In Java, the basics of encapsulation is the class, although the class will be examined in great detail later in the book. The following brief discussion will be helpful now. A class defines the structure and behavior, data, and code that will be shared by a set of objects. Each object of a given class contains the structure and behavior defined by the class, as if it were stamped out by a mold in the shape of the class. For this reason, objects are sometimes referred to as instances of a class. Thus, a class is a logical construct. An object has physical reality. When you create a class, you will specify the code and the data that will constitute that class. Collectively, these elements are called members of the class. Specifically, the data defined by the class are referred to as member variables or instance variables. The code that operates on that data is referred to as member methods or just methods. If you are familiar with C/C++, it may help to know that what a Java programmer calls a method, a C/C++ programmer calls a function. In properly written Java programs, the methods define how the member variables can be used. This means that the behavior and interface of a class are defined by the methods that operate on its instance data. Since the purpose of a class is to encapsulate complexity, there are mechanisms for hiding the complexity of the implementation inside the class. Each method or variable in a class may be marked private or public. The public interface of a class represents everything that external users of the class need to know or may know. The private methods and data can only be accessed by the code that is a member of the class. Therefore, any code that is not a member of the class cannot access a private method or variable. Since the private members of a class may only be accessed by other parts of your Since the private members of a class may only be accessed by other parts of your program through the class public methods, you can ensure that no improper actions take place. Of course, this means that the public interface should be carefully designed not to expose too much of the inner workings of a class. Inheritance. Inheritance is the process by which one object acquires the properties of another object. This is important because it supports the concept of hierarchical classification. As mentioned earlier, most knowledge is made manageable by hierarchical, that is, top-down classifications. For example, a golden retriever is part of the classification dog, which is in turn part of the mammal class, which is under the larger class animal. Without the use of hierarchies, each object would need to define all of its characteristics explicitly. However, by using However, by the use of inheritance, an object need only define those qualities that make it unique within its class. It can inherit its general attributes from its parent. Thus, it is the inheritance mechanism that makes it possible for one object to be a specific instance of a more general case. Let's take a closer look at this process. Most people naturally view the world as made up of objects that are related to each other in a hierarchical way, such as animals, mammals, and dogs. If you wanted to describe animals in an abstract way, you would say they have some attributes such as size, intelligence, and type of skeletal system. Animals also have certain behavioral aspects. They eat, they breathe, and sleep. This description of attributes and behaviors is the class definition for animals. If you wanted to describe a more specific class of animals, such as mammals, they would have more specific attributes, such as the type of teeth and mammary glands. This is known as subclass of animals, where animals are referred to as mammals. Superclass. Since mammals are simply more precisely specified animals, they inherit all of the attributes from animals. A deeply inherited subclass inherits all the same attributes from each of its ancestors in the class hierarchy. Inheritance interacts with encapsulation as well. If a given class encapsulates some attributes, then any subclass will have the same attributes, plus that it adds as a part of its specialization. This is a key concept that lets object-oriented programs grow in complexity linearly rather than geometrically. A new subclass inherits all of the attributes of all of its ancestors. It does not have unpredictable interactions with the majority of the rest of the code in the system. Polymorphism. Polymorphism, from the Greek meaning many forms is a feature that allows one interface to be used for a general class of actions. The specific action is determined by the exact nature of the situation. Consider a stack, which is a last in, first out list. You might have a program that requires three types of stacks. One stack is used for integer values, one for floating point values, and one for characters. The algorithm that implements each stack is the same, even though the data being stored differs. In a non-object-oriented language, you would be required to create three different sets of stack routines, with each set using different names. However, because of polymorphism in Java, you can specify a general set of stack routines that all share the same names. More generally, the concept of polymorphism is often expressed as the phase 1 interface multiple methods. The phrase one interface multiple methods. This means that it is possible to design a generic interface to a group of related activities. This helps reduce complexity by allowing the same interface to be used to specify a general class of actions. It is the compiler's job to set the specific action, that is, method, as it applies to each situation. You, the programmer, do not need to make this selection manually. You need only remember and utilize the general interface. Extending the dog analogy, a dog's sense of smell is polymorphic. If the dog smells a cat, it will bark and run after it. If a dog smells its food, it will salivate and run to its bowl. The same sense of smell is at work in both situations. The difference is what is being smelled. That is the type of data being operated on by the dog's nose. The same general concept can be implemented in Java as it applies to methods within a Java program. Polymorphism, encapsulation, and inheritance work together. When properly applied, polymorphism, encapsulation, and inheritance combine to produce a programming environment that supports the development of far more robust and scalable programs than does the process-oriented model. A well-designed hierarchy of classes is the basis of reusing the code in which you have invested time and effort developing and testing. Encapsulation allows you to mitigate your implementations over time. Encapsulation allows you to migrate your implementations over time without breaking the code that depends on the specific interface of your classes. Polymorphism allows you to create clean, sensible, readable, and resilient code. Of the two real-world examples, the automobile more completely illustrates the power of object-oriented design. Dogs are fun to think about from an inheritance standpoint, but cars are more like programs. All drivers rely on inheritance to drive different types, subclasses of vehicles. Whether the vehicle is a school bus, a Mercedes sedan, a Porsche, or the family minivan, drivers can all more or less find and operate the steering wheel, the brakes, and the accelerator. After a bit of after a bit of gear grinding, most people can even manage the difference between a stick shift and an automatic because they fundamentally understand their common superclass, the transmission. People interface with encapsulated features on cars all the time. The brakes and gas pedals hide an incredible array of complexity with an interface so simple you can operate them with your feet. The implementation of the engine, style of brakes, and the size of the tires have no effect on how you interface with the class definition of the pedals. The final attribute, polymorphism, is clearly reflected in the ability of car manufacturers to offer a wide array of options on basically the same vehicle. For example, you can get an anti-lock brake system or traditional brakes, power or rack rack and pinion steering, and 4, 6, or 8 cylinder engines. Either way, you can still press the brake pedal to stop, turn the steering wheel to change direction, and press the accelerator when you want to move. The same interface can be used to control a number of different implementations. As you can see, it is through the application of encapsulation, inheritance, and polymorphism that the individual parts are transformed into the object known as a car. The same is also true of a computer. By the application of object-oriented principles, the various parts of a complex program can be brought together from a cohesive, robust, maintainable whole. As mentioned at the start of this section, every Java program is object-oriented, or put more precisely, every Java program involves encapsulation, inheritance, and polymorphism. Although the short example programs shown in the rest of this chapter and in the few chapters may not seem to exhibit all of these features, they are nevertheless present. As you will see, many of the features supplied by Java are part of its built-in class libraries, which do make extensive use of encapsulation, inheritance, and polymorphism. A first simple program. Now that the basic object-oriented underpinning of Java has been discussed, let's look at some actual Java programs. Let's start by compiling and running the short sample program shown here. As you will see, this involves a little more work than you might imagine. Comment. This is a simple Java program called this file example.java. Class, example. Comment. Your program begins with the call to main. Public static void main, string arguments. Within. System out, print line. This is a simple Java program. End quote. Semicolon. Close class, close program. Note, The descriptions that follow use the standard Java SE8 development kit, JDK8, which is available from Oracle. If you are using an integrated development environment, IDE, then you will need to follow a different procedure for compiling and executing Java programs. In this case, consult your IDE's documentation for details. Entering the program. For most computer languages, the name of the file that holds the source code to a program is immaterial. However, this is not the case with Java. The first thing that you must learn about Java is that the name you give a source file is very important. For this example, the name of the source file should be example.java. Let's see why. In Java, a source file is officially called a compilation unit. It is a text file that contains, among other things, one or more class definitions. For now, we will be using source files that contain only one class. The Java compiler requires that a source file use the .java file name extension. As you can see by looking at the program, the name of the class defined by the program is also example. This is not a coincidence. In Java, all code must reside inside a class. By convention, the name of the main class should match the name of the file that holds the program. You should also make sure that the capitalization of the file name matches the class name. The reason for this is that Java is case sensitive. That at this point, the convention that file names correspond to class names may seem arbitrary. However, this convention makes it easier to maintain and organize your programs. Compiling the program. To compile the example program, execute the compiler javac, specifying the name of the source file on the command line as shown here, javac example.java. The javac compiler creates a file called example.class that contains the bytecode version of the program. As discussed earlier, the Java bytecode is the intermediate representation of your program that contains instructions the Java virtual machine will execute. Thus, the output of javac is not code that can be directly executed. You actually run the program. To actually run the program, you must use the Java application launcher called Java. To do so, pass the class name example as a command line argument as shown here, Java example. When the program is run, the following output is displayed. This is a simple Java program. When Java source code is compiled, each individual class is put into its own output file named after the class and using the .class extension. This is why it's a good idea to give your Java source files the same name as the class they contain. The name of the source file will match the name of the .class file. When you execute Java, as just shown, you are actually the name of the class you want to execute. It will automatically search for a file by that name that has the .class extension. If it finds the file, it will execute the code contained in the specified class. A closer look at the first sample program. Although example.java is quite short, it includes several key features that are common to all Java programs. Let's closely examine each part of the program. The program begins with the following lines. Quote, "This is a simple Java program. Call this file example.java." End quote. End of comment. This is a comment. Like most other programming languages, Java lets you enter a remark into a program's source file. The contents of the comment are ignored by the compiler. Instead, a comment describes or explains the operation of the program to anyone who is reading it. It's source code. In this case, the comment describes the program and reminds you that the source file should be called example.java. Of course, in real applications, comments generally explain how some part of the program works, or what a specific feature does. Java supports 3 styles of comments. One shown at the top of the program is called a multi-line comment. This type of comment begins with / asterisk and ends with */. Anything between these two comment symbols is ignored by the compiler. As the name suggests, a multi-line comment may be several lines long. The next line of code in the program is shown here. Class example, open bracket. This line uses the keyword class to declare that a new class is being defined. Example is an identifier that is the name of the class. The entire class definition, including all of its members, will be between the opening curly brace and the closing curly brace. For the moment, don't worry too much about the details of a class except to note that in Java, all program activity occurs within one. This is one reason why all Java programs are at least a little bit object-oriented. // Your program begins with a call to main. This is the second type of comment supported by Java. A single line comment begins with a // and ends at the end of the line. As a general rule, programmers use multi-line comments for longer remarks and single-line comments for brief line-by-line descriptions. The third type of comment, a documentation comment, will be discussed in the comments section later in this chapter. The next line of the code is shown here. Public static void main string args, open bracket. This line begins the main method. As the comment preceding it suggests, this is the line at which the program will begin executing. All Java applications begin execution by calling main. The full meaning of each part of the line cannot be given now, since it involves a detailed understanding of Java's approach to encapsulation. However, since most of the examples in the first part of this book will use this line of code, let's take a brief look at each part now. The public keyword is an access modifier, which allows the programmer to control the visibility of class members. When a class member is preceded by public, when that member may be accessed by code outside, then that member may be accessed by code outside of the class in which it is declared. The opposite of public is private, which prevents a member from being used by code defined outside of its class. In this case, main must be declared as public since it must be called by code outside of its class when the program is started. The keyword static allows main to be called without having to instantiate a particular instance of the class. This is necessary since main is called by the Java virtual machine before any objects are made. The keyword void simply tells the compiler that main does not return a value. As you will see, methods may also return values. If this seems a bit confusing, don't worry. All of these concepts will be discussed in detail in subsequent chapters. As stated, main is the method called when a Java application begins. Keep in mind that Java is case sensitive. Thus, capital M main is different from lowercase main. It is important to understand that the Java compiler will compile classes that do not contain lowercase main. Method. But Java has no way to run these classes. So if you had typed capital M main instead of lowercase m main, the compiler would still compile your program. However, Java would report an error because it would be unable to find lowercase main method. Any information that you need to pass to a method is received by variables specified within the set parentheses that follow the name of the method. These variables are called parameters. If there are no parameters required for a given method, you still need to include the empty parentheses in lowercase main. There is only one parameter, albeit a complicated one. The string args declares a parameter named args, which is an array of instances of the class string. Arrays are collections of similar objects. Objects of the type string store character strings. In this case, args receives any command line arguments presented when the program is executed. This program does not make use of this information, but other programs shown later in this book will. The last character on the line is open bracket. This signals the start of the main lowercase m parentheses body. All of the code that comprises a method will occur between the method's opening curly brace and its closing curly brace. One other point, lowercase main is simply a starting place for your program. A complex program will have dozens of classes, only one of which will need to have a lowercase main method. To get things started, furthermore, in some cases, you won't need main at all. For example, when creating applets, Java programs that are embedded in web browsers, you won't use main, since the web browser uses a different means of starting the execution of applets. The next line of code is shown here. Notice that it occurs inside main. System.out.println, quote, "This is a simple Java program," close end of quote, close parenthesis, semicolon. This line outputs the string "This is a simple Java program," followed by a new line on the screen. Output is actually accomplished by the built-in println method. In this case, println displays the string which it's passed into it. As you will see, println can be used to display other types of information too. The line begins with system.out. While too complicated to explain in detail at this time, briefly, system is the predefined class that provides access to the system, and out is the output stream that is connected to the console. As you have probably guessed, console output and input is not used frequently in most real-world Java applications. Since most modern computing environments are windowed and graphical in nature, console I/O is used mostly for simple utility programs, demonstration programs, and server-side code. Later in this book, you will learn other ways to generate output using Java, but for now, we will continue to use the console I/O methods. Notice that the println statement ends with a semicolon. All statements in Java end with a semicolon. The reason is that the other lines in the program do not end in a semicolon. This is that they are not technically statements. The first close bracket, close curly brace in the program ends the main, and the last close curly brace ends the example class definition. A second short program. Perhaps no other concept is more fundamental to a programming language than that of a variable. As you may know, a variable is a named memory location that may be assigned a value by your program. The value of a variable may be changed during the execution of the program. The next program shows how a variable is declared and how it is assigned a value. The program also illustrates some new aspects of console output. As the comments at the top of the program state, you should call this file example2.java. Comment. Here is another short example. Call this file example2.java. Class example2, open curly brace, public static void main, string args, open curly brace. Int num. Comment. This declares a variable called num. Num equals 100. Comment. This assigns num the value 100. System out print line, quote, this is num, end quote, plus num, semicolon, end of statement. Num equals num times 2, semicolon, end of statement. System.out.print the value of num times 2 is, close quote, semicolon, end of statement. System out print line num, close curly brace, end of program. When you run this program, you will see the following output. This is num 100. The value of num times 2 is 200. Let's take a close look at why this output is generated. The first new line in the program is shown here. Int num, semicolon, comment, this declares a variable called num. This line declares an integer variable called num. Java, like most other languages, requires that variables be declared before they are used. Following this general form of a variable declaration, type var name. Here, type specifies the type of variable being declared, and var name is the name of the variable. If you want to declare more than one variable of the specified type, you may use a comma-separated list of variable names. Java defines several data types, including integer, character, and floating point. The keyword int specifies an integer type in the program. The line num equals 100, semicolon, comment, this assigns num the value 100, assigns to num the value 100. In Java, the assignment operator is a single equal sign. The next line of code outputs the value of num preceded by the string, this is num, end of quote. System.out.println, quote, this is num, end quote, plus num. In this statement, the plus sign causes the value of num to be appended to the string that precedes it, and then the resulting string is output. Actually, num is first converted from an integer into its string equivalent, and then concatenated with the string that precedes it. This process is described in detail later in this book. This approach can be generalized using the plus operator. You can join together as many items as you want with a single print line statement. The next line of code assigns num the value of num 2 times. The next line of code assigns num the value of num times 2. Like most other languages, Java uses the asterisk operator to indicate multiplication. After this line executes, num will contain the value 200. Here are the next two lines in the program. System out print, quote, the value of num times 2 is, end quote, semicolon, end of statement. System.out print line num, semicolon, end of statement. Several new things are occurring here. First, the built-in method print is used to display the string the value of num times 2 is. This string is not followed by a new line. This means that when the next output is generated, it will start on the same line. The print method is just like printline, except it does not output a new line character after each call. Now, look at the call to printline. Notice that num is used by itself. Both print and printline can be used to output values of any of Java's built-in types. Two control statements. Although Chapter 5 will look closely at control statements, two are briefly introduced here, so they can be used in example programs in Chapter 3 and 4. They will also help illustrate an important aspect of Java, blocks of code. The if statement. The if statement works much like the if statement in any other language. Further, it is syntactically identical to the if statements in C and C++ and C#. Its simplest form is shown here. If condition statement semicolon end of state. Here, condition is a Boolean expression. If condition is true, then the statement is executed. If the condition is false, then the statement is bypassed. Here's an example. If num is less than 100, system.out println, quote, num is less than 100, end quote, semicolon, end of statement. In this case, if num contains a value that is less than 100, the conditional expression is true, and println will execute. If num contains a value greater than or equal to 100, then the println method is bypassed. As you will see in Chapter 4, Java defines a full complement of relational operators which may be used in a conditional expression. Here are a few. Less than, greater than, equal to. Notice that the test for equality is the double equal sign. Here is a program that illustrates the if statement. Comment. Demonstrate the if. Call this file ifsample.java. Class, if sample, open curly brace, public static void main string args, open curly brace. Int x y semicolon end of statement. X equals 10 semicolon end of statement. Y equals 20 semicolon end of statement. If x is less than y, system.out.println x is less than y, end quote, semicolon end of statement. X equals x times 2, semicolon end of statement. If x is equal to y, system.out.println x is x now equal to y, end quote, semicolon end of statement. X equals x times 2, semicolon end of statement. If x is greater than y, system.out.println x is now greater than y, end of quote, semicolon end of statement. Comment, this won't display anything. If is x is equal to y, system.out.println, you won't see this, end quote, semicolon, end of statement, close curly brace, close curly brace. The output generated by this program is shown here. X is less than y, x now equal to y, x now greater than y. Notice one other thing in this program, the line int x y semicolon end of statement declares two variables, x and y, by use of a comma-separated list. The for loop. As you may know from your previous programming experience, loop statements are an important part of nearly any programming language. Java is no exception. In fact, as you will see in Chapter 5, Java supplies a powerful assortment of for loop constructs. Perhaps the most versatile is the for loop. The simplest form of the for loop is shown here. For initialization, semicolon, condition, semicolon, iteration, statement, semicolon. In this common form, the initialization portion of the loop sets a loop control variable to an initial value. The condition is a Boolean expression that tests the loop control variable. If the outcome of that test is true, the for loop continues to iterate. If it is false, the for loop terminates. The iteration expression determines how the loop control variable is changed each time the loop iterates. Here is a short program that illustrates the for loop. Comment, demonstrates the for loop. Call this file, quote, for test.java. Class, for test. Open curly brace. Public static void main string args, open curly brace. Int x, semicolon, end of statement. For x equals 0, semicolon, x is less than 10, semicolon, x equals x plus 1. System.out.println dot println, this is x plus x. Close curly brace, close curly brace. This program generates the following output. This is x0, this is x1, this is x2, this is x3. This is x4, this is x5, this is x6, this is x7, this is x8, this is x9. In this example, x is the loop control variable. It is initialized to 0 in the initialization portion of the for. At the start of each iteration, including the first one, the conditional test x is less than 10 is performed. If the outcome of this test is true, the println statement is executed, and then the iteration portion of the loop is executed, which increases x by 1. This process continues until the conditional test is false. As a point of interest, in professionally written Java programs, you will almost never see the iteration portion of the loop written as shown in the preceding program. That is, you will seldom see statements like this: x equals x plus 1. The reason is that Java indicates a special increment operator which performs this operation more efficiently. The increment operator is plus plus. That is two plus signs back to back. The increment operator increases its operand by 1. By use of the increment operator, the preceding statement can be written like this: x plus plus semicolon, end of statement. Thus, the for in the preceding program will usually be written like this: for x equals 0, semicolon, x less than 10, semicolon, x plus plus. You might want to try this, as you will see the for loop runs exactly the time as it did before. Java also provides a decrement operator, which is specified as minus minus. This operator decreases its operand by 1. Using blocks of code. Java allows 2 or more statements to be grouped into blocks of code, also called code blocks. This is done by enclosing the statements between opening and closing curly braces. Once a block of code has been created, it becomes a logical unit that can be used in any place that single statement can. For example, a block that can be a target for Java's if and for statements, consider this if statement. If x is less than y, open curly brace, comment, begin a block, x equals y, semicolon, end of statement, y equals 0, semicolon, end of statement, close curly bracket, comment, end of block. Here, if x is less than y, then both statements inside the block will be executed. Thus, the two statements inside the block form a logical unit, and one statement cannot execute without the other also executing. The key point here is that whenever you need to logically link two or more statements, you do so by creating a block. Let's look at another example. The following program uses a block of code as the target of a for loop. Comment: demonstrates a block of code. Call this file, quote, block test.java. End of comment. Class block test. Open curly brace. Public static void main string args. Open curly brace. Int x y semicolon end of statement. Y equals 20 semicolon end of statement. Comment: the target of this loop is a block. For x equals 0 semicolon x is less than 10 semicolon x plus plus open curly brace system.out.println this is x end of quote plus x semicolon end of statement. System.out.println quote this is y end of quote plus y semicolon end of statement. Y equals y minus 2 semicolon end of statement. Close curly brace, close curly brace, close curly brace. The output generated by this program is shown here. This is x 0, this is y 20, this is x 1, this is y 18, this is x 2, this is y 16, this is x 3, this is y 14, this is x 4, this is y 12, this is x 5, this is y 10, this is x 6, this is y 8, this is x 7, this is y 6, this is x 8, this is y 4, this is x 9, this is y 2. In this case, the target of the for loop is a block of code and not just a single statement. Thus, each time the for loop iterates, the 3 statements inside the block will be executed. This fact is, of course, evidenced by the output generated by the program. As you will see later in this book, blocks of code have additional properties and uses. However, the main reason for their existence is to create logically inseparable units of code. Lexical issues. Now that you have seen several short Java programs, it is time to more formally describe the atomic elements of Java. Java programs are a collection of whitespace identifiers, literals, comments, operators, separators, and keywords. The operators are described in the next chapter. The others are described next. Whitespace. Java is a free-form language, which means that you do not need to follow any special indentation rules. For instance, the example program could have been written all on one line, or in many other strange ways you felt like typing it, as long as there was at least one whitespace character between each token that was not already delineated by an operator or separator. In Java, whitespace is a space, tab, or new line. Identifiers. Identifiers are used to name things, such as classes, variables, and methods. An identifier may be any descriptive sequence of uppercase and lowercase letters, numbers, or the underscore and $ characters. The $ characters is not intended for general use. They must not begin with a number, at least lest they be confused with a numeric literal. Again, Java is case sensitive, so value is different from identifier value with just one uppercase V. The other value being all uppercase. Some examples of valid identifiers are arg_temp, count, a4, money test, this underscore is underscore okay. Invalid identifier names include these: to count, I dash temp, not slash okay. Note, beginning with JDK8, the use of an underscore by itself as an identifier is not recommended. Literals. A constant value in Java is created by using a literal representation of it. For example, here are some literals. 100, 98.6, quote, single quote, X, quote, this is a test, end of quote. Left to right, the first literal specifies an integer. The next is a floating point value. The third is a character constant. And the last is a string. A literal can be used anywhere a value of its type is allowed. Comments. As mentioned, there are 3 types of comments defined by Java. You have already seen 2, single line and multi-line. The third type is called a documentation comment. This type of comment is used to produce an HTML file that documents your program. The documentation comment begins with a / and ends with */. Documentation comments are explained in the appendix. Separators. In Java, there are a few characters that are used as separators. The most commonly used separator in Java is the semicolon. As you have seen, it is used to terminate statements. The separators are known in the following table. Parentheses, used to contain lists of parameters in method definition and invocation, also used for defining precedents in expressions containing expressions in control statements and surrounding cast types. Braces, used to contain the value of automatically initialized arrays, also used to define block of code for classes, methods, and local scopes. Brackets, used to declare array types, also used when differentiating array values. Semicolon, terminates statements. Comma, separates consecutive identifiers in a variable declaration, also used to chain statements together inside a for statement. Period, used to separate package names from subpackages and classes, also used to separate a variable or method from a reference variable. Colons, used to create a method or constructor reference added by JDK8. There are 50 keywords currently defined in the Java language. See Table 2.1. These keywords, combined with the syntax of the operators and separators, form the foundation. Abstract, assert, boolean, break, byte, case, catch, char, class, const, continue, default, do, double, else, enum, extends, final, finally, float, for, goto, if, implements, import, instance of, int, interface, long, native, new, package, private, protected, public, return, short, static, strict FP, super, switch, synchronize, this, throw, throws, transient, try, void, volatile, while. Of the Java language, these keywords cannot be used as identifiers. Thus, they cannot be used as names for variables, class, or method. The keyword const and goto are reserved but not used. In the early days of Java, several other keywords were reserved for possible future use. However, the current specification for Java defines only the keywords shown in Java 1 is shown in Table 2.1. In addition, the keywords Java reserves the following true, false, and null. These are values defined by Java. You may not use these words for the names of variables, classes, and so on. The Java class libraries. The sample programs shown in this chapter make use of two of Java's built-in methods, println and print. As mentioned, these methods are available through system.out.system. This is it through system.out.system is a class predefined by Java that is automatically included in your programs. In the larger view, the Java environment relies on several built-in classes, libraries that contain many built-in methods that provide support for such things as I/O, string handling, networking, and graphics. The standard classes also provide support for a graphical user interface, GUI. Thus, Java as a totality is a combination of the Java language itself plus its standard classes. As you will see, the class libraries provide much of the functionality that comes with Java. Indeed, part of becoming a Java programmer is learning to use the standard Java classes. Throughout Part 1 of this book, various elements of the standard library, classes, and methods are described as needed. In Part 2, several class libraries are described in detail.